Hello. In this video, I'm going to discuss section 7.1, the topics of which are graphing and functions. So first of all, let's go over the system of the coordinate plane. So I'm going to start by drawing a number line. So this is meant to be a real number line. That goes from negative infinity to infinity. All real numbers are represented here. I'm going to add a little bit of scale by putting a 0 in the middle and adding a few integer marks. So some positive numbers on the right, some negative numbers on the left. And I've capped it with an arrow on both ends to indicate that this goes on and on forever. So next, I'm going to add another number line. This one's going to run vertically. It'll pass right through that 0 mark on that horizontal number line. Again, I'll cap this with arrows to show that it continues on forever. And as I move up this number line, I'm going to add some positive integers for scale. And going down, I'll add some negative integers, -2, 3, -4, -5, -6. All right, so this horizontal number line I'm going to call the x-axis. The vertical number line I'll call the y-axis. The point where the two intersect, so right here, this is the origin. And these two lines that intersect at a right angle make quadrants. In the top right, we call this quadrant 1. Going counterclockwise, this is quadrant 2, quadrant 3, and quadrant 4. And I can locate any point in this plane, so in this two-dimensional space, by using coordinates, one that gives me a position on the x-axis, and a second that gives me a position on the y-axis. So for instance, this point here in the plane, that in order to locate that point, if I move over 3 units along the x-axis and then up 4 units on the y-axis, I'll find that point. So this has coordinates 3, 4. This first number is called the x-coordinate, and the second number is called the y-coordinate. And together, these make up an ordered pair. And an ordered pair is sufficient to locate any of the points in this plane. And by plane, I just mean this two-dimensional space, where we have one dimension, which is left and right, and a second dimension, which is up and down. So let's get a little practice in locating some points in the plane. So I'm going to add some ordered pairs, and we'll label them A, B, C, and D. So point A has ordered pair 2, 5 for coordinates. Point B has -1, 4 for its coordinates. C has -4, -2, and D has -5, 0. So let's find these points in our plane. So 2, 5. So I'll go over 2 and then up 1, 2, 3, 4, 5. So I'll put a point here and label that A. For point B, the x-coordinate is -1, so I'll go to -1 on the x-axis and up 4, so about right here. That would be point B. Point C, both coordinates are negative, so I go to -4 along the x-axis, so over here, and then down 2 on the y-axis, and that gives me point C. And then point D has a coordinates, ordered pair coordinates -5 and 0. So -5 is here, and since the y-coordinate is 0, I'll neither go up nor down, but that point sits right on the x-axis, so there's point D. So notice that in quadrant 1, we end up with both coordinates are positive, the x-coordinate and the y-coordinate. So just like with A, where we had positive 2 and positive 5, those will live in the first quadrant. For points in quadrant B, quadrant 2, such as point B, the x-coordinate is negative and the y-coordinate is positive. I'll just make a little note here. The x is negative, the y is positive. In the third quadrant, so that's over here, as with point C, both the x and the y coordinate are negative. I'll make a little note, negative, negative. And we didn't plot a point over here, but a point in this quadrant, such as, let's say, this guy, I'll call that E. So the x-coordinate for E is 4, and the y-coordinate is negative 3. So just like all points in quadrant 4, this has a positive x-coordinate and a negative y-coordinate. So that's how we can find points in the coordinate plane. So next I'm going to talk about graphs of equations. So we're not going to be just looking at single points, but entire sets of points. So graphs of equations. So a relationship between two variables or two quantities can be expressed as an equation in two variables. So an example of a relationship that's expressed as an equation in two variables could be something as simple as y equals x plus 2. So this is an equation that describes a relationship or defines a relationship between the two variables x and y. So if I want to understand this relationship a little bit better, I might look at specific values of x and y. So for instance, negative 3. When x is negative 3, what's its partner? What's the y value in this relationship? So in order to find that, I can replace x by negative 3. So negative 3 plus 2 is negative 1. A little reminder, if you think about on your number line, where this is 0, negative 1, negative 2, negative 3, there's a little, yeah. If I start at negative 3 and add 2, I'll be going 2 places to the right, I'll end up at negative 1. I could also find values really for any real numbers, or partners for any real number x. But let's just look at some of these. If I take negative 2 and add 2, I'll get 0. Negative 1 plus 2 is positive 1. 0 plus 2 is 2. 1 plus 2 is 3. And this would be 4 and 5. So these are just some of the ordered pairs in this relationship between x and y defined by the equation y equals x plus 2. Now, I have a list here of just 7 ordered pairs, but there are actually infinitely many ordered pairs that are defined by this relationship. So even though I was picking integer values, I could have also said 1/2 plus 2. So I could have come up with the ordered pair 1/2 and 1/2 plus 2, which is 2.5. Or I could have taken a decimal, such as 0.1, and 0.1 plus 2 is 2.1. So if I want to define the entire relationship, a convenient way to do that is to look at the graph of the equation. And I can use this table that I've created to plot ordered pairs and maybe then get a sketch of the entire graph. So let me just add some markers here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And negative 1, negative 2, negative 3, negative 4, negative 5. These go on and on forever. This is my x-axis. This is my y-axis. So negative 3, 1, 2, 3, and negative 1. So here's the first point. Negative 2, 0 is here. Negative 1, 1 is here. 0, 2, and so forth. I'll sketch a line that connects all these, but it goes on forever. I'll cap each end with an arrow to make sure that that's obvious. This is not a line segment, it's actually an entire line. So this relationship defined by this equation is represented here by this line that goes through these points. Okay, so next let's talk about functions. So if, oops, let me switch out here. Make sure we have a marker that works. Try this one more time. Maybe I'll just use this blue one. If an equation in two variables, oftentimes we'll use x and y. Not necessarily. You could use, these are arbitrary. In an equation in two variables, if an equation in two variables yields exactly one value of x, of y, for each value of x, then we can say y is a function of x. Now, in the last example, where I had this equation y equals x plus 2, notice that for any value of x I picked, there was exactly one value of y that corresponded. So I didn't have to decide between two values when I filled in this table. I knew for sure that negative 3 plus 2 only equals negative 1. So that's what we mean when we say that each value there's exactly one value of y for each value of x. Just to give you a counter example there, something that would not be a function. If I said y equals the plus or minus square root of x, then consider if I said, what happens when x is positive 4? Well, notice this says plus or minus square root. So when I plug in 4, there is a negative square root, which is negative 2, and a positive square root, which is 2. So there are two y values that are paired with this one x value. So this is not a function. But in the previous example where we said y equals x plus 2, that is a function. So if we're sure that we have an equation that is a function, we can use function notation. So I'm going to use an f. We won't always use f, but here I am. And then a pair of parentheses. So this says f of. So we have a function of, in this case x, is defined by x plus 2. So here I have this written as an equation. Here I have it written as a function. So let's look at another example where I have a function f of x defined as x minus 6. So just to get a little bit of practice using function notation, if I want to evaluate this function for a particular value of x, I might write f of, and then a particular value, maybe 9. So to evaluate this, I would replace the x with the value 9, so that equals 9 minus 6, which I can evaluate. 9 minus 6 is 3. I could also say f of 0, in which case I would take 0 and subtract 6, and that would be negative 6. Or f of negative 2. So that would be negative 2 minus 6. I'm already at negative 2. I subtract 6. I go 6 spaces to the left, and I end up at negative 8. So as far as how this relates to ordered pairs, the 9 was an x value, and its partner is the y value. In this case, the this evaluating the function at 9 yields 3. So I just found out that in this relationship there's the ordered pair 9, 3. Here we found that there's the ordered pair 0, negative 6, and here we have negative 2, negative 8. So we could use these values or other ordered pairs to get a graph of this function. So I know I have the ordered pair 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 2, 3, 9, 3. I have got 0, 1, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Got another ordered pair here. Negative 2, negative 8 would be off my charts. Let me just add a few more values. I'll make a table where I have x and the function evaluated at x. So what happens when I plug in positive 1? So if I take 1 minus 6, I'll have negative 5. If I take 3 and subtract 6, I'll have negative 3. So let me add those. I've got 1, negative 5, 3, negative 3, and then I can connect these and cap my ends with arrows to show that that goes on and on forever. So this is the graph of the function f of x equals x minus 6. Oops. I'll show you the rest of that. Let's do one more. This time I'm going to just switch out my notation. I mean, it's still function notation, but instead of using f of x, I'm going to call this h of x. Sometimes you'll use g of x, f of x, h of x. H of x is defined as negative x squared plus 3. And I want to get a graph of this function. So I'm going to start with a table where I look at particular values of x and then find h of x. I was about to write f of x, but that's an h of x. So let's look at negative 3, negative 2, negative 1, 0, 1, 2, and 3. I'm going to actually start in the middle. If I take 0 and square it, 0 times 0 is still 0. When I take the opposite of that, still 0. Add 3, 0 plus 3 is 3. I'll move down here to the next value, which is 1. 1 squared is 1. And I'll take the negative of that and then add 3. I'm not going to write this out so it's clear. 1 squared is positive 1, but then I have to take the opposite of that. So negative 1 plus 3 is 2. Here I'm taking the negative of 2 squared and adding 3. The reason I'm doing this, if you think about your order of operations, we square or really execute any exponential before we look at the sign. This is actually, you could think of this as being negative 1 times x squared plus 3. So I evaluate the exponential before I do the multiplication or take the opposite. So 2 squared is 4. The opposite of 4 is negative 4. Negative 4 plus 3 is negative 1. 3 squared is 9. Negative 9 plus 3 is negative 6. And negative 1 squared. A negative times a negative is a positive. So negative 1 squared is positive 1. I take the opposite, and that's negative 1. Negative 1 plus 3 is 2. Negative 2 squared is 4. I take the opposite. That would be negative 4. Negative 4 plus 3 is negative 1. And then lastly, negative 3 squared is 9. I take the opposite. That's negative 9 plus 3. And again, I get negative 6. So looking at the plane here, 1, 2, 3, 4, 5, 6. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. And I'll just use the lines that are on the paper for the markers. Well, actually, let me just put a few tick marks to highlight this. So -3, -6. I'm going to use a different color here. -3, -6. This is -1, -2, -3, -4, -5, -6, and -1, -2. So about here, that's -3, -6. That's for this ordered pair. -2, -1 is here. That's this pair. -1, 2 is here. And then the point 0, 3 is there. I've got 1, 2, 2, -1, and 3, -6. So when I connect all these, I end up with a shape we call a parabola. And so this is not a line, but rather this is a curve. When we have a square, in this case, when our input variable is squared, the x value is squared, you'll end up, rather than a straight line, you'll have this nice curved, almost like an upside down U shape. So I'll follow this up with a second video from 7.1 where I show you a few applications. So be looking for part 2 of 7.1.